Today, I will talk about my recent work in collaboration with Christophe Dalapa, Gregor Kelling, Raphael Young, Jack Neff, and Rusuke Jinno, Heinrich Rubia, mostly Daisy. Sorry. Let me start with happening of Higgs boson from IHC and more recently, the first direct detection of gravitational waves from the merger of two black holes. Both high-energy gravitational physics has entered a new precision era. So that the physics can also play a role in about 100 gravitational wave events has been observed by LIGO, Virgo, and Canberra detectors. And the majority of them are binary black hole system, but there are also two binary neutron star like this, and two mixed binary neutron star black hole system. And as we know, a gravitational wave provides us with new way to understand many fundamental problems in physics. And for this purpose, precision predictions for waveform templates are very important. Waveforms will be far more complex and carry more information than expected. Improved modeling will be needed for extracting gravitational wave information. Capes-1 made this in particular for upcoming future observations like Einstein telescope and LISA. Precise theoretical prediction for the motion of gravitational wave source are very crucial in interpreting observation data and maximizing discovery potential. As shown in this picture, so evolution of a binary black hole system consists of three phases, typically like in spiral, merge, and rundown. And in merge phase, the interaction is extremely strong. And so in this case, we can only use the numerical relativity simulation to solve Einstein equations. And for rundown phase, the black hole perturbation theory is an efficient and powerful way. For in spiral phase, this phase covers a large number of cycles, and therefore numerical simulation are normally computationally expensive. This phase, because the wake is and in two bodies is very small, so perturbation theory works. For example, we can compute correction order by order in velocity way, or more directly in Newton constant G. This is just Feynman's post-Newtonian or post-Minkowski expansion. My talk focuses more on post-Newtonian expansion for two-body dynamics, and because in this expansion is more suitable for the use of quantum field theory approach. And in PME expansion, the first two order has been known about 40 years ago. And very recently, the use of cloud physics tools has greatly transformed this field. And the collaborator, they computed the first 3 PM result using sky geometries. And later, it was confirmed by our classical calculation. More recently, we finished the calculation of 4 PM dynamics for binary system. In the I will explain this in detail. With this slide, I introduce our formalism briefly. So in the inspiral phase, the gravitational field is weak, and we can write the metric in this way. Here, eta is just a flat space metric, and the fluctuation h mu nu just describe gravitational fields. Basic idea is that using effective field theory approach, we can construct an effective action for the two-body systems via integrating gravitational fields h mu nu. Here, this part just Woodley actions that describe two black holes or neutron stars. Here we take a point particle approximation, and we can add some higher derivative operators to describe effects. And this is Einstein-Hilbert action that describe interaction between two bodies. And then we can compute effective action in integration theory. Effective Lagrangian. The leading order just the Lagrangian for we found it's more easy to compute to solve the equation of motion. The standard way to use Feynman diagrams. So in our formalisms, we have the vertex between Woodley and gravitons. Because we do not quantize Woodley, we just include Woodley as a source of path integral. So Feynman works like this, and if we expand the Hilbert-Einstein actions, we can get the vertices of graviton to a number of points. And because we study only classical physics, so we can use side point approximation in path integral to calculate classical contributions. So as a result, because we use quantum field theory, but we care about only a classical contribution. So our formalism quantum methods and the classical fields. We use quantum technology, so the computation tools are very powerful and systematic. Okay. And because we are interested in only classical physics, so every step keep classical and computations keep simple. So with Feynman diagrams, finally, our computation for variables is reduced to computation of Feynman integrals. For example, this is the input that is momentum change from initial state to final state. So it has this structure. This part just Fourier integral that transform result from momentum space to the space of impact parameter. And this is loop integrals. So here, B just graviton propagators that normally has retarded form. But if we are interested in only conservative part, we can simply use Feynman propagators. And because the Woodley is almost unsure, so they appear as delta functions. So in this integral, every loop momentum is always accompanied by a delta function that can simplify calculations. The integral depends on three external vectors. Here, u1 and u2 just the initial velocity of two bodies, and the q is momentum transfer. They satisfy these relations. So finally, this integral just a function of single visible gamma to any loop order. So finally, with our formalisms, we found the multi-loop technology can be directly used to solve gravitational problems. So with these slides, I would like to give a minimal introduction about applied physics tools we used to study gravitational problems. So to compute this type of integral, first for delta functions, we can use first entirety to understand delta function as ordinary propagators. This trick was initially introduced to compute cross-section for Higgs product, and then standard loop integral technology came. And then we can use IP reduction to reduce Mine integral as a linear combination of small number of integrals. And at this moment, so mining computer program has been available, like reduce, fire, Kra, and NIT IBP. So after reduction, our task becomes to compute a small set of mass integral. For this purpose, we just found the method of differential equations is this kind of differential equations. We can determine the value of integrals. System of differential equations can be transformed into this form. That is where epsilon is factorized, and if Q is a rational coefficient, in this way, the solution can be written in terms of multiple logarithms to any order in epsilon. And we found that from three-loop lifting integral also appear in differential equations. So that make we cannot find the canonical forms. But finally, we found the differential equations are still very powerful for compute elliptic integrals. And finally, so boundary conditions for our integral can be computed in post-Newtonian limit using a method of reading developed by Simonov and friends. So finally, very nicely in our framework, post-Minkowski dynamics can be bootstrapped from post-Newtonian data. So now I tell you the first example. This is I use our framework formalism to compute inspiring dynamics of two bodies in next order. In this order, because we study only classical physics, so we just need to compute only 7 diagrams. And finally, our computation reduced to compute this type of integrals. This is some two-loop integrals, and we just found the reduction and evaluation for this can be performed in a standard way. Finally, this is our result for inputs at this order. In this result, we have rational functions and logarithms. And this result was the first classical confirmation for computation by Zhengwen and collaborators. And with this type of integrals, we can also compute like finite size effects induced by tidal force. So let's continue looking at the next to leading order for non-spinning binary. We need also still a small number of diagrams. Just need about and in this order, we need to compute some three loop integrals like this. So for this case, we found the standard program like nitrate together with fire is still powerful to reduce this kind of integrals. And for conservative part of dynamics, we just need to use operators in this. But if we want to compute full dynamics, including radiative effects, in this case, we have to use the retard propagator, and the integral has much less symmetries. In this case, we found about 1,000 mass integrals. And then we compute, we evaluate mass integral via differential equations. We found the majority of integral, for majority of integrals, the canonical differential equations still work. And in this case, solution can be solved in terms of polylogarithms. And for elliptic integrals, we found we also finally managed to compute them. This is an example of elliptic integral 3x3 blocks involved in our calculations. We found in the leading order in epsilon expansion. So this system can be transformed into a third order ordinary differential equations. Just found, for example, with really solve this. And for higher order, with the knowledge of this solution, we can construct epsilon factorized form, and finally we can solve this kind of differential equations. For example, this is the result. Sorry, this is the result for inputs at this order. So in this result, in addition to rational functions and logarithms, it also features dialog and complete elliptic integrals. And this is the result was the first analytic result for full dynamics of binary. And in the low energy limit, our result is in perfect agreement with the post-Newtonian calculations by Bini, Damore, and Troll and collaborators. And for conservative part, our result is exactly same with computation from Amtu's method by Zhengwen and collaborators. Very recently, two different groups confirmed our analytic result has been checked numerically by two groups. In this plot, Alessandra Bonanno's group compared our analytic result with numeric simulations. In this plot, so this dashed line is for a numeric simulation, and different color line reference different PM order. This is 1 PM, 2 PM, 3 PM, 4 PM. And from this plot, we found higher order higher PM calculation improved precision significantly. And more recently, Damore and collaborator compared our result include radiation effects with numeric simulation for two-body scattering, and they found surprisingly good agreement between two methods. So inclusion physics has already very useful to improve theoretical prediction for gravitational observers. And based on ideas, effective field theory and multi-loop technology, we have developed an efficient framework and obtained a new result for the dynamics of two-body system to next to leading order. And I finished my talk with this outline. The era of gravitational wave science is just starting, and in the future, new discovery highly rely on the precision of result at G5th order in the 5 p.m. order is highly desirable for next generation observations like Einstein telescope and LISA. For this purpose, we have to compute this type of four-loop integrals. Here, so we have 4 data functions in the color propagator and 9 real propagators and 9 irreducible scalar products, in total 22 indexes. And in gravity, normally the degree of numerator is so high. This makes IPT reduction like extremely complicated. And in this kind of integrals, so more complicated function beyond the polylogs may be involved. This also we need new technology from applied physics community, and I'm very happy to learn from you. That's wonderful workshop. Thanks for attending.
Thank you very much.
Thanks.
Very interesting talk. Questions? I have some naive questions too, but first.
Can you go back 2 or 3 slides where you have this agreement with numeric? Yeah, this one, the left plot. So agreement with numerical relativity. I think this is the black curve, right?
Yes.
And where is your prediction? Like, is it precisely spot on, or is this sort of the power expansion in post-Minkowski? Okay, so you mean to illustrate the convergence as you go to higher orders in post-Minkowski expansion?
Yes.
Okay. Thanks.
Sorry if I missed it. So what exactly do you show in this plot? What is chi and B and R? Sorry.
Scattering angle.
Scattering angle.
The impact between 2 bodies.
Oh, okay. So you just in general 2 bodies in this. Okay, I'm still trying to make the connection. So what can you actually? How can you test this in a gravitational wave signature? Is it in a waveform somewhere in a ringing?
Yes.
Sorry about this. Very naive question.
Yes. Or 2 body scattering case, but we can do analytical information at the information for bound space.
Okay.
So for bound space, cycle or future experiment can observe.
So how would it then this show up exactly? Do you have in the ringing signature? No, but can you show how it would look like with future sensitivity?
For LIGO, prediction to sweeping order.
Okay.
For future experiments, they need like 5 p.m. and even 6 p.m.
Oh, okay. Thank you. You have a question?
Yeah, thanks for this wonderful talk. So you didn't mention anything about spin, like how do you incorporate the classical spin here?
So here,
Hey, thanks again for the talk. I had again a question on the plot. So, like on the left side, one can see that there is very good progress getting to the numerical, but the right-hand side is really spot on. So, what's the difference? And it's just this left has only the conservative, and the right has.
So, for this case include only conservative.
Exactly. So basically, when you add the emission, you get really the nice agreement with the numerics.
Yes.
Okay, and how do you separate these two components, these conservative and radiative?
In our computations, so different can be surprised by boundary conditions in post-Newtonian expansion. For example, for potential modes has this kind of behavior. So this components means energy component, and this is momentum components. For radiation modes has this kind of radiation modes is almost on-shear, right? That has this kind of scaling behavior. And for conservative parts, we can use Feynman propagators, and that just can contain potential modes and two radiation modes. But for radiation case, we have considered all different readings.
Okay, so when you do potential, you can simply work with Feynman propagators, while for the other one, you need to do this the I epsilon properly for retarded.
Yes.
Okay. Okay, thanks.
So you have shown essentially the diagrams that you are looking at. I wanted to understand what was the class of diagrams. So you have the two world lines.
Yes.
And those are the two bodies, and they just they behave almost like Wilson lines in some sense. Only you do allow for scattering. Right? I'm saying Wilson lines only because you have these linear propagators, and in our calculations we tend to associate linear propagators with
Yes.
Wilson lines. So there is and then you have the gluons in the gravitons in the middle.
Yes, yes.
And what kind I see, for example, only planar diagrams. Is that a constraint that you have?
No, actually. Yes, it's three. I'm below three levels. We have only for none of that. For 4 levels, we have non-planar.
You also have non-planar.
For example, we can change this node to here.
Okay.
It becomes a non-planar.
So you simply have the complete calculation.
Yes.
2 line. This is a 2-to-2 scattering. In which only gravitons are exchanged, and you literally have all the diagrams to compute.
Yes.
And what is special about it is this measure in which on the lines the propagators are linear, and you have those delta functions.
Yes.
Okay.
Other questions? Okay, so let's thank again the speaker again, and I think we have coffee at 3:30, right? Sven? I think this is perfect.
So except for the coffee, have a nice weekend, everyone. Enjoy Florence if you stay, and wherever you are, have a nice trip.